Alright. Are you ready, Space Marine? I feel it's important you know this, whether I like the fact that you know it or not. Inside of here, I'm going to teach you how to create the universe. You need to do it again. You need to start over with your crew, as far as I'm concerned. If I'm there, you rats is mine. So we're going to learn how to create the universe. Right here. See? You know what this book is? This is a Horseman Code book. Get it out. Alright. So inside here, let's recreate the universe. I don't know what it is. It might be square, it might be circle. So let's just rip this up. Let's take the book and rip it up. We're going to roughly make this out to a circle. It's a C4 detonation gone off in there. Let's try to keep it in the wheelhouse, a circle at least. Around. Alright. But whatever had happened, however you rip that off, that'll be irrelevant. It won't matter. It could be the most globular, flopped out shape that you could ever possibly imagine. The universe probably didn't do that in space. Okay. Probably didn't have any really globular states that changed out that orientation, which we'll get back into. I'll show you another example of it that I did a second ago. We're working it out. That will give you one of the numbers. Hopefully I can recreate this here so this comes out. Well, that's natural log 0. It's the universe. It is natural log 0, 1. I am 1. 0. So basically fusion out there, right? This is the universe, it's the star, it's a planet, it's everything in between that, because what we'll be doing in this natural log is creating 1, right? So we want to make sure this fold is somewhere in the neighborhood. Now this is lined paper, and I did pretty close to a circle, so when we fold this is our first measurement. This is our first radiant of the universe, not from center mass, but from me looking to the black hole, Mars, right? This is our universe. We can't, the matter should be the same, log x, natural log x, natural log y, the same material in there, hydrogen in its wave function. But then there will be a decay state that happens. Well, isn't there a spectrum to hydrogen? There sure is, bud. And if just hydrogen in space, there's nothing really decaying it short of it emitting its vibration and decaying into a point where it disbands into heat. All that hydrogen just turned into heat in the universe, expanding the universe, continuing. And as it did so, there were moments where closer to whatever core or the star or whatever you're dealing with says that at certain points, phased away from the distance, it will have an increase or a decrease of relative perspective. See, up and down, I1, I1, I2, I2 in a circuit design of that center mass. Now, why is that important? Well, in log 1, we'll do that to make the distinguishation of what is capital form R over whatever nonsense we have here. Hydrogen on the top because it's a lighter element, and based on what we know of gravity, we didn't know anything. You are back to crudes as far as I'm concerned, and you're going to go back to this piece of paper that describes that, and so you might have to make I1, I2, I2 determinations of whether hydrogen is here and it raises, because hydrogen actually has a state where it doesn't drop. And against it, if hydrogen and helium, both lighter than air, increase, then if a balloon full of hydrogen and a balloon full of helium, a buoyant force is going to drive that balloon full of hydrogen up higher, faster than the balloon with helium in it. And in that way, we have this fractal. Now, what's interesting about that is, see, we just created a wormhole that opened up the warp entities right just immediately off the hop off with one fold. So I already have 4 parts. 1, 2, 3, 4 in itself make 5. And we're going to play with that 0, 1, 1, 2, 3, 0, 1, 2, 1, 2, 3, without 0. Without 0, we just have the line. What is 1? This is what we're towing, the Gaussian, the radial, so on and so forth. Get some names in there, spend some time, plan out your timeline. Let's dive in, shall we? So we know roughly that is the top and the bottom. Now, obviously, by looking at this, remember how I said some globular states were being involved? Right there at the crest at the top that this isn't right. So we're going to have to make sure that we fold this in orientation that we can see that extra point. We're going to round off inside of that to just what was the two inside points here, which happen to be this angle. Otherwise, I would have chose the other angle first. But we're trying to keep it clean here, and we're going to fold that up to the other edge.
How does it affect my game?
That should give us 4 equally measured lines. Now, they might be more or less. That's okay. We're not that far into the game yet. Now, how can we make this other connection so we can actually make a perfect square out of this situation? So that way I can describe a radiant by a distance. In that distance of radial, there's more power because I'm taking the round off and I'm backing it down. I'm saying that quantified in this distance, it is not the total distance of that. This would become 1. Clean, it will fit inside of the distance or magnitude, velocity, voltage limits that system will do. If I go a little over, that might be alright. If I go a little under, it might be okay. I'm thinking on thirds or something. You can't be over a third on it or something, or under 66 or something. I don't remember. So when we're dealing with this, well, how do I then actually figure out an angle? Is it the vertical? Do I fold horizontally? Well, you can from center mass. But remember, we started inverted IH, or I, or capital form R, lower form of R's. Those prime and unprime states are natural logs. We're just saying that it's log theta as the original line here, which isn't an angle, but it is a 90 degree. We're just going to plow through some of this. Now, there's a couple ways to do that. Because we don't know that measurement yet, we can't really distinguish whether these lengths are truly equal or not. Inches, centimeters, at log 3, log half. That's going to be a problem, so we have to figure out what fold actually determines what this is. Well, there's a couple of different ways. We have points that are increment, and we know no matter what the distance of those lines are, that they will always be lined up with each other at this 90 degree angle. We don't really have the ability to say we want these 4 points essentially to line up 8 times. So let's just fold it in such a way. I'll get this right. Try to get these folds in here. Make sure fold it correctly. We'll make sure that all this is lined up so our points where our folded edge met the other edge all line up. As straight as you possibly can. Just make sure we get that right here. You can fold them a couple different ways. Just make sure you get that fold in there. And now they won't be perfect. Remember, the universe isn't perfect. There's a C4 blast out there in the core of a neutron star, man. But we're starting to get some folds inside here. We know it has to do with hydrogen, that fold inside of this system. So now we have... we need another one. So now what do we know? Now we got some values. We got 1, 2, 3, 4 axes to deal with here. 1, 2, 3 axes to deal with here. Excuse me. Which is your x, your y, and your z, or x prime, or so it is 4. But they're all one dimension. They're all still doing things. They might have different lengths from the edges of those things. We don't have anything to measure yet. You can't just measure from center mass at that point in time and say that is 1 inch. We have to figure out what 1 inch is first. The size of your subject space matters. We're trying to keep it something in hand for why it should be in that area. So... if we utilize that fold, now we have the ability to actually say, inside of there, we create some dishing, some black hole stuff. But we don't actually want to do that. We want to fold this so that the outer edges create a straight line down here by similar points of how that affects part of the system here. 1/2 first, I think. Okay, make sure we get that and this. So that way we can fold this such that on that curvature we'll actually have a straight fold or something close to it, I think. And you want to replicate that fold, this dish type, this cone in Penn's row, if you will, to actually give us what is real close. Now, it may not be perfectly straight at that point in time, but we can straighten that off. We would say, all right, that's the angle, that's where I'm close to be. Let's just fold that over to connect those points. Which you could have done. I guess you can just fold it over there to connect the points. But we're trying to keep it as square as possible. Doing that extra step will help you keep it square. Because mathematically, it's mechanical at that point instead of you just trying to use creative inspiration about it. And I'm not exactly sure. I know what I'm doing here. But what we can get. From those points. Is 1. And I'm going a bit fast there. And I hadn't quite hit the... We got the X, we got the Y, and as you need a Z, you might not need that other fold to determine it, because once you get one of them folds and you can creep it like that, it may X, Y, and Z accordingly. Not mirrored, it'll X, Y, and Z, and that's that first bit of the thirds, that X, Y, and Z axis of X, because now we know that we have a 90-degree angle from that fold. We have to. It must do that. That gives us X and Y, because alphabetically X, X prime, or excuse me, alpha, beta, the first decay state. Without this element, I cannot make this element. Gaussian. I want you to play with that and then recreate that, whether, now that we have this, now we have the axis is on the side, we have a fourth, you know, right? Because we can, it's easily folded to the measurement here. We have the quarters that we need to determine what this is. From there, I think the other methodology would be this, right? Now that we have actually this rough to inch square, that'll be okay. Roman foot and imperial foot are different. They are actually, if you take a measurement, stick to it, a Roman foot I think is like 11 inches. It's either 11 or 13. But imperial, when the king got a hold of it, I couldn't have brickwork done that way, because from one site to another result, you will have a building that is not correct. And you needed some way to determine that. Now, why that is what that is still is irrelevant. You could do this again and still, well, the outer edge of the universe wasn't quite right to it. You're right. There's no guarantee. This circle was the one they made. We just made this one. If they started with this, then obviously that's going to be a different square. But by units, why it does what it does, as long as we use this system to fractalize it like that, that it should measure out to a bunch of different physics stuff that goes into it at least. And I know it certainly works practically with that brick. If you do this, why it is, when some kid asks you why imperially you're going to change the measurement to that many measurements, 1, 2, 3, 4, 12, to a foot, this tool becomes something practical at that level where you can describe that system. You get a little woke about it and you're in the math class, you're trying to close the deal with some hippie, astrology chick out there in the bar. It might be a fun way to describe some of those functions and deal with your universe. That I told you that this stuff was fusion, I wasn't kidding. I told you everything's a hadron collider.